So lesson one was on relations, and a special type of relation is called a function. When we look at these ordered pairs here in this relation F, we have 1, 5, 2, 6, 3, 7, 4, 8, and 5, 9. When we see this, for every x, you can only have one y. So basically, the x's can't be repeated. So this first one, f, is a function. But if we look at g, 1, 1, 1, negative 1, for every x, there is more than one y, 4, 2, 4, negative 2. So this second relation, g, is not a function. But we have studied relations, and when we have x and y values and we plot ordered pairs, these are both relations. So a function is kind of special. It is a special kind of relation. For each member of the domain, there is only one member in the range. In other words, a function is a set of ordered pairs in which no two ordered pairs have the same first coordinate. I've always heard it said, for every x, there can only be one y. And we'll talk about a little bit more about what that means in a minute. First of all, relations and functions may not always be expressed as a set of ordered pairs. So we saw that before. Not every function is going to be a distinct set of ordered pairs. So sometimes there may be a rule which assigns an output value to y. So we might have an equation to tell us what the y values would be as long as we know what the x values are. This rule may be expressed in many ways. So as an equation, f could be expressed as y equals x plus 4. So we've seen equations that look like that with y. It kind of looks like y equals mx plus b, for example. And then our x values might be 1, 2, 3, 4, 5. Mapping notation, that's one that I don't see as often. I think this is common, and you've seen equations that look like this before. We mostly are going to use now function notation. So this is the one that you'll see most often. F of x equals x plus 4. F of x. What I really want you to notice is that f of x replaces y when we're using function notation. So I want you to always kind of think about that f of x replaces y. This is the same as y. The reason we write f of x is because we can sub in any of these x values right there, and we would find out what the y would equal. So it's kind of just a different notation to show you that values do become subbed in for x here, and we would find out what our y is. So for example, let's just look below. The above notations are interchangeable and can be used as is convenient. In each of the notations, the ordered pairs for the function f can be found by inserting each value from the domain into the rule. For example, if f of x equals x plus 4, and x is an element of 1, 2, 3, 4, 5, then for example, we would say f of 1. So if x is 1, then we would put a 1 in for x. 1 plus 4 is 5. Another way to think about that is if x is 1, y is 5. So it looks like a new notation and it looks really strange, but this is saying, hey, if x is 2, put a 2 in for x. 2 plus 4 is 6. So therefore y would equal 6. If x is 2, y is 6. So these are giving us ordered pairs, really. We're finding out, okay, if my x is a 1, what is my y? If my x is a 2, what is my y? If my x is a 3, this is what you get. And this is how you'd find a set of ordered pairs. So example 1, this is always a little confusing to students at first, but once you get the hang of it, remember that g of x is just function notation, but that is really replacing the y. We're just suggesting that you're going to sub in different values for x. So if our function g of x equals 3x squared minus 2x plus 1, what is g of negative 4? It just means sub in negative 4 for x. So g of negative 4 would be 3 times negative 4 squared minus 2 times negative 4 plus 1. Anywhere I see an x, I'm going to replace it with a negative 4. So 3 times 16 plus 8 plus 1, 48 plus 8 plus 1, which gives me 57. This one is obviously a little harder. It's oh, what if our x becomes a 2t? This is what you sub in for x. So we're going to go 3, and then 2t is going to become our x. Whatever is in here is what becomes substituted in for x. So this one we're not going to be able to get just a numerical answer, but this would be 3 times 4t squared minus 4t plus 1. And this is function notation, and it's just what we sub in here for x. So 12t squared minus 4t plus 1. And that's all we can do for that because we don't have a value for t. They can get a little bit trickier. If this is our function here, this is h of x. Obviously, x can't equal 0. That's a restriction. We've seen that before. This is asking you, what if x is x minus 4? So it seems odd, but if h of x equals x plus 5 over 3x, anywhere you see an x is going to be replaced with x minus 4. It's always a good idea when you sub in to sub in using brackets, because it helps you to see if you're supposed to be using the distributive property. In the numerator, I'm just collecting like term over 3 times x minus 4. And I see that x can't equal 4 if we were going to state the restriction. Over here, instead of x, I'm going to write 6 over z. Okay, so this is just to see, these are just testing some of your math skills. I'm going to put 6 over z where the x is, and 3 times 6 over z. Then in order to add 6 over z plus 5, we'd have to have a common denominator. So 6 over z plus, if I want 5 to be over z, I'm going to have to multiply the numerator also by z. In the denominator, I can just multiply 3 times 6, which is 18, over z. So what does this mean? It looks really scary. This is a lot of fractions divided by, so we have a fraction divided by another fraction. I could probably put my numerators together, 6 plus 5z over z, divided by 18 over z. Okay, what are we going to do with that? We have a lot of fractions. You know what makes this a lot easier? I'm going to show you this trick that I really like. This division sign between two fractions here can also be written as a division sign like that. So could I just write 6 plus 5z over z divided by 18 over z? And I think it looks so much easier when you write it that way, because I know I'm supposed to invert and multiply times z over 18. And my z's actually cancel each other out. So I end up with 6 plus 5z over 18. And I do know that here I had restrictions in the denominators, not in the numerator. So I know that z can't equal 0. So just remember, if you ever see a lot of fractions, a fraction in the numerator and denominator, that this division line here could be written as that symbol, and it just makes it so much easier to do. So this is just function notation, and what it means when you have a function h of something, and it's just subbing in that something for the variable x. We can test to see if something is a function. So at the beginning we talked about how a function is special. It's a special type of relation. And for every x, there can only be one y. It doesn't always have to have distinct points. We can have a straight line, for example, where we have all the points are connected, and a straight line is a function as long as it's not vertical. So there are two tests to determine if a relation is also a function. We can do the vertical line test, which I really like. This is the one I like the most because it's really easy. And you would have a graph. If any vertical line crosses the graph of a relation in one and only one point, then the relation is a function. You cannot draw a vertical line through a function at any point of the graph. If you hit 2 points, it is not a function. You can only go through 1 point when you draw a vertical line. There's also an equation test if a value of x can be found which produces more than one value of y. When substituted into the equation, then the equation does not represent a function. We'll do one of those as well when we just try and look at the equation to determine whether or not we have a function. So this example 3, questions like this I don't mind. Which of the following two graphs illustrate a function? So if you imagine here, I know we have distinct points and they're not connected, but anywhere here, if I'm drawing any vertical lines, I never hit more than 1 point. So because of the vertical line test, I'm going to just, because I have a graph, I can just do the vertical line test. And we can determine that this is a function. So remember, you can only hit 1 point. When we look at part B, if I imagine drawing a vertical line anywhere through the graph in part B, I end up hitting more than 1 point. So that right there tells us that this is not a function. Okay, we've had graphs of parabolas before. They were called quadratic functions. If I imagine a vertical line coming down, I would only ever hit 1 point. So quadratics are functions. But if your parabola, if we graph the inverse of that, maybe it would be something that looks like this. That would be not a function. So graphs aren't bad. Graphs are easy to picture. Okay, with the last example, what we're going to do is just look at equations and try and understand from the equation if we have a function or not. So this, just first, I just wanted to go over this one more time. These points, 1, 2, 2, 2, 3, 2. So 1, 2 would be here, let's say, and 2, 2 would be over here, and 3, 2 would be beside it. So if we had 3 points like that, I know that the y's are repeated over and over again, but that is still a function because the x values are not repeated. So this one over here would be a function. If I had 2, 1, that would be here, and then 2, 2, I would be above it, and 2, 3, I would be above it. This would not be a function. So the x values cannot repeat. How does that help? So if we were given a simple equation, something like a linear equation, for example, like y equals 2x plus 1. When we're looking at this equation, can we sub something in for x that would give us more than 1 y? For every x, you can only have 1 y. So if my x is 2, 2 times 2 is 4, plus 1 is 5. But if my x is 3, for every x, I'm only going to get 1 y. So we know that this is going to be a function. The equation test says if a value of x can be found which produces more than one value of y, when substituted into the equation, then the equation does not represent a function. So let's just look at this equation first. I would like to isolate the y. Maybe divide both sides by -4. So we still have y squared equals 9x squared minus 36 over 4. I would have to take the square root of both sides in order to isolate y. So that is the positive or negative square root of 9x squared minus 36 over 4. So what that means is when you take the square root of something like the square root of 9, that gives me positive or negative 3, because negative 3 times negative 3 is also 9. So here's what I want you to notice about this equation. If I subbed a number in, like 2 or 3 for x, I would have one x that I'm subbing in, like x equals 2, but I would end up with two different values for y. So this is not a function. So I might say there would be two y values for a single x value. Therefore, this is not a function. There would be different y values for a single x value, so it is not a function. Sometimes we do have restrictions with our equation. So for example, if I think about the restrictions for this, I see that that's a difference of squares. So just our denominator, we're just kind of thinking this through if this is a function or not. Our denominator might be x squared plus 4 times x squared minus 4. This one I can't factor any further, but this one over here, I can make, that's another difference of squares, so x plus 2, x minus 2. So these are our restrictions. There's nothing I can sub in here that would give us a value of 0. I could sub 0 in here, I could sub a negative number in here, I could sub a positive number in here. This is not going to be a restriction, but I do see that x cannot equal negative 2 or positive 2. So as long as x doesn't equal negative 2 or positive 2, this would be a function. I could sub in different numbers for x. So if I sub in x is positive 1, I could put positive 1 in here. This would be 1 to the 4th minus 16. I would get a single value for y. If I sub in a negative 1, I would get a different value for y. So for any value of x other than these, this is a function.